Hello everyone, I am B. Sister Reddy from ECEA section. Today, I am going to give a seminar about autocorrelation and cross-correlation functions. This is from the subject probability theorem and stochastic process, where this topic is used for analyzing signal relationships and patterns effectively. In this seminar, I am going to give a brief explanation about introduction and definitions of autocorrelation and cross-correlation functions and their mathematical formulas, properties, applications, and graphical representations. Let's move on to the introduction. Here, autocorrelation and cross-correlation are fundamental concepts in the field of probability theory and stochastic process. These techniques are widely used in signal processing, statistics, and data analysis to understand the relationships between within a signal or between a multiple signals over a time. Here, autocorrelation analyzes a signal with itself of a delayed with itself delayed version, which helps in identifying repeating patterns or periodic signals. Whereas cross-correlation, on other hand, measures the similarity between two different signals as one is shifted in time related to other. These concepts are essential for analyzing time series data, detecting signal patterns, and estimating time delays between signals. Understanding these correlations allows researchers and engineers to make informed decisions in various applications such as communications, image processing, and pattern recognition. Let's see definitions of autocorrelation and cross correlations. Autocorrelation is defined as the measure of similarity between a signal and a delayed version of itself over varying time lags, whereas it is used in detecting repeating patterns or periodic signals within the same dataset as I said before. And the cross correlation measures the similarity between two different signals as one is shifted in time related to other. It is useful for identifying the degree of similarity and the time delay between two signals. These definitions form the basis for analyzing temporal relationships in stochastic processing and signal processing. Their mathematical formulas. The mathematical formulas formulation of autocorrelation and cross-correlation provides a quantitative measure of signal similarity. For autocorrelation, the formula is Rx of tau equals to E of x of t into E of t plus tau, which calculates the expected value of product of signal and its delayed version. Here E represents expected value and x of t is the signal and tau is the time delay. This formula helps in identifying periodicity and signal stability over a time. And also for cross correlation, the formula is Rxy of tau equals to E of x of t into y of t plus tau, which evaluates the expected value of product of two different signals, one of which is time shifted. This is particularly useful in applications where the alignment or synchronization of signals is critical, such as in communication systems and time delay estimation. These formulas are integral to theoretical framework of stochastic processes and widely applied in practical scenarios. Let us see a few properties of autocorrelation and cross-correlation. They possess several important properties that make them valuable in signal analysis. Autocorrelation is symmetric, which means it is also said to be even. Mathematically, Rxx of tau equals to Rxx of minus tau. And there is another property which where autocorrelation typically has its maximum value at zero lag, indicating the highest similarity when the signal is compared with itself without any delay. This property is useful for identifying the presence of periodic components in a signal. And for cross correlation, while not necessarily symmetric, but also there is a property where Rxy of tau equals to Ryx of minus tau, which provides the insights into the similarity between two signals, and it is instrumental in estimating the time delay between them. It is particularly useful in applications where the signal alignment is necessary, such as in radar and sonar systems. Both correlation or linear operations can be computed efficiently using algorithms like Fourier transform. Understanding these properties helps in interpreting the results of correlation analysis and applying them effectively in various domains. Let us see applications of the autocorrelation and cross correlation. Autocorrelation and cross correlation have a wide range of applications across different fields. In signal processing, autocorrelation is used to detect periodic signals and analyze noise characteristics. It is also employed in time series analysis to identify trends and seasonal patterns. Cross correlation is crucial in pattern recognition, where it helps in matching templates and detecting features in images. In communication systems, cross correlation is used for synchronization and time delay estimation between transmitted and received signal. Also, image processing applications utilize these correlations for tasks such as image registration and motion detection. Additionally, these techniques are applied in econometrics, neuroscience, and meteorology to analyze temporal relationships in data. Their versatility and effectiveness make them indispensable tools in both theoretical research and practical implementations. Uh, and the graphical representations of autocorrelation and cross correlation, where the graphical representations of autocorrelation and cross correlation provide intuitive insights into the behavior of signals over time. Autocorrelation graphs typically plot correlation values against time lag, showing peaks at intervals corresponding to periodic components in the signal. A prominent peak at zero lag indicates strong similarity with the original signal without any delay in time, where cross-correlation graphs display the correlation between two signals as one is shifted in time, revealing the time delay at which the signals are most similar. These graphs are essential for visualizing signal relationships and are commonly used in exploratory data analysis. They also help in identifying patterns and detecting anomalies and validating theoretical models. For these graphical representations and visualizations, we use tools like MATLAB, Python, and built-in functions to generate these plots, and making it easier for researchers and engineers to interpret and utilize correlation data effectively. Let us have a quick summary of what we have discussed about autocorrelation and cross correlation. In summary, autocorrelation and cross correlations are powerful techniques for analyzing signals and stochastic process. Autocorrelation helps in understanding the internal structure of a signal by comparing it with its delayed versions, while cross correlation evaluates the similarity between different signals over time. Their mathematical formulations provide a robust framework for quantitative analysis, and their properties enable effective interpretation of results like symmetric property and maximum at zero lag, these kind of properties. These correlations find applications in diverse fields such as signal processing, image analysis, communication systems, and time series forecasting. Graphical representations further enhance understanding by visualizing the temporal relationships in data. Mastery of these concepts is essential for uh, anyone working in the domain of probability theory and stochastic process, as they form the foundation for advanced analytical techniques and practical implementations. Uh, and also, there is a point where the relationship between correlation and convolution. There's these are similar when the tau T represents tau, and tau is a negative value of T, which means E of x of tau into x of tau minus T, which is also can be expressed in convolution form. And this is an further topic, autocorrelation and cross correlation. Thank you.